Hello guys, so now we finish our IP core that calculates the histogram and the contrast adjustment, okay? So now we are going to switch to Vivado, okay? Where we're going to use with the Zynq those two IP cores, okay? We also going to learn how to use the broadcast stream, where you can actually split or share the same stream with two IP cores. And then we jump to Zynq SDK, where we're going to write the software version of those algorithms and compare to the version working in hardware. Okay, hope you guys enjoy it, and let's go. So guys, how we can now mix the histogram and the contrast adjustment in our system, okay? Imagine that this can be with a microblaze or the Zynq itself. Probably going to do in the Z board, because I basically forgot to bring the board here at home. And imagine this. We have our processor, okay, and we have our DMA, which actually sends streams to this and this guy, okay. In our case, we want to calculate the histogram at the same time that we do the contrast adjustment, because basically we don't want to have one DMA for every stream IP that you have, okay. So what we're going to use here, the magic here is this broadcast. This stream broadcast block, okay? Basically what it does is simply repeat the stream to two IP cores, and it is stopped when both of them finish, okay? And this is basically how we're going to create our system. We're going to have the DMA, okay? The DMA is going to send the image stream through this broadcast. At the same time, we're going to send stuff for the histogram block that we created in the previous videos, and the contrast adjustment block that we created here, okay? For sure, these guys here need parameters that are going to be calculated when you finish the histogram. So basically, in this case here, we actually are not doing the two stuff in parallel, because we need the histogram, then we do the contrast. But this is basically to show how you can have multiple axis stream IP cores and just one DMA, okay? So let's now jump to Vivado and see how we can create these guys and do a system that actually do something useful, okay? So guys, now we're going to merge all these IP cores, okay? The histogram and the contrast adjustment, okay? And we're going to create a project with Zynq using those IP cores. So we're going to use here our Z board. Maybe, yes, I think it's enough. It's basically the thing that will be new in this project is that now we're going to use the broadcast, the axis stream broadcast. This will be new. We never used it up to now. And this is the way that we're going to use to have one stream that is going to be shared, okay, between two IP cores. So basically everything keep the same. We add here a Zynq. At some point we're going to add a DMA as well, and basically simple stuff as we were doing up to now, okay? So let me just check which users, Leonardo, which directory I add this stuff. So basically we want our histogram, and we also want our stretch, which is the histogram stretch, okay? So we add here a DMA, we are going to configure our DMA to do simple transfer 23. We want to allow an aligned transfer. Our data type will be 8 bits. By the way, it's a grayscale image. Now we're going to enable the high performance port of the Zynq. So let's now just connect those guys here. Well, some information about the broadcast. Actually, the broadcast is going to share the stream. Let me open up this guy a little bit. Is going to switch to share the stream. Okay, let me add the histogram and the histogram stretch, and it will be easy for you guys to see. Okay, let's add as well the broadcast. So basically, this guy here, okay, has only, I mean, the DMA has only one output to these guys. So what we need to do, we basically need to come here. Oh, whoops. Come to this guy here, and this guy will come here, and this other guy will come here. Okay. The histogram actually is going to connect to a BRAM port, so we don't need to, I mean, the histogram will not output any stream, so we can come from this guy and connect directly here. Okay. Let me just organize this a little bit more. The histogram stretch has an Axelite interface, okay, where we actually set the min and max values. Our histogram also have, because we want to set the start and stop. Sorry, I say start and stop, but it's not start and stop, and start and is idle. Okay, it actually has an interrupt port if needed, but it's not the case now. We're not going to use the interrupts to indicate that that the IP core done its calculation. Okay, so now we're going to add, actually Vivado will connect a BRAM here, but we want this BRAM block to also be available for the Zynq, so we're going to change it to true dual port RAM. Okay, we're going to add a BRAM controller. This BRAM controller does not need to be dual port because we only have one port available. So we come here, connect to this guy. Let's just bring this guy here, and we're going to connect this to our AXI general purpose port. Okay. Well, since that we're quite done, so basically, again, let me just bring the, what is the DMA? Let's bring this guy here, and this guy here. So basically, the DMA will output the image, okay, and this guy here is going to broadcast to the input of the histogram and the contrast adjustment, the histogram stretch. Okay, as this guy has no stream output, we can give the output of this guy directly to the input of the DMA, and that's it. Now we just validate the design just to check if we let something missing. We forgot something. Actually, this is the clock signal and the reset signal of our broadcast we missed. So let's validate again, and if all is right, we're going to create an HDL wrapper of all these, and we're going to generate our bit stream. Maybe there is one more point that that actually one of our subscribers asked, always to put a timer to compare the results in software and in hardware. So let's put here an AXI timer. put 64-bit mode because we want a big timer. So we also connect this guy here. Well, now it seems that everything is fine. We're going to maybe validate again just to check, and we're going to create the HDL wrapper, and then we jump to the code, which is where we're going to actually have stuff to do. Okay, so now we come here, sources, we actually asked to create an HDL wrapper. Which is done. Just one more word about the broadcast. Okay, so we split the stream between this guy and this guy. If this guy is slower than this one or vice versa, the axis stream is actually going to block the stream until both finish. Okay, so basically the broadcast will synchronize them both. Okay, so you don't need to care if one finish first or the other one. They will both finish at the same time. They will both receive the same stream. Okay, so we save it, and we go to generate bit stream, and I'm going to pause the video because this will take probably 15 minutes or something like this, and then we switch to the Zynq SDK where we're going to do the job. Okay, so the bitstream generation is done. At this point, we're going to export our bitstream to Zynq SDK, and we can start from there. Okay, so we just come and launch the Zynq SDK. So now we're going to concentrate more on the software part, and I'm going to show you guys how to use those IP blocks and also how to measure time. So guys, we start from the project already done. Okay, I choose to do this way because it would be simpler to explain, even for me, because I can see the code and explain at the same time. Okay, so let's read it together. Basically, this part here is where we define the headers. Okay, that import the generated drivers that Vivado HLS create for us. Okay, by default, Vivado HLS will create drivers for IP cores that have AXI-Lite, slave, or AXI master. Okay, this guy here is just the image of Lena, but in terms of an array. Okay, I created a kind of script that does that for us. Okay, that you give an image, okay, an array, and it converts for you to a C code array. These guys here is just where we define where our DMA will work. Basically, we choose to have a faraway address because we don't want the DMA to start to write in our memory, in our code space. Okay, because then the code will be totally erratic. Okay, those guys here is where we basically define the some arrays that we store the histogram calculated in software, the image output calculated in software, I think in hardware as well we're going to do this, and the image in vector that we're going to give to the DMA to read our image. Okay, this guy here is where is the address of the BRAM block that we calculate the histogram. Okay, if we come here on our project in Vivado, we can see that let me just do a zoom out here. We can see that the histogram, okay, after he finishes his job, he's going to store the value here in a BRAM, and we use a AXI BRAM controller that is going to access this BRAM block. Okay, and his address is here, 4000 big value, and basically it's this. Okay, so here is where the histogram in hardware will send the values. Those functions here are just to actually to initialize the DMA, the histogram core, and the histogram stretch. Basically, this is this will be kind of always the same. This is the way that we initialize those generated drivers. Okay. What more? We create in order to compare how fast the hardware version is with the hardware version, with the software version. Sorry, we create the histogram and the histogram stretch in software. We're going to measure the time. By the way, here we use as well an axis timer. I don't know where he is. Let us check. Okay, here we have an axis timer that we use to calculate the time of the time elapsed for the functions to complete. Okay, and we execute our stuff. So here we initialize. We created here a wrapper for the axis timer. By the way, the source code of all these guys are going to be available at the end of this Vivado HLS course. So here we actually execute the histogram in software, okay, but we put in between start timer and stop timer, sorry, because we want to calculate the elapsed time that the histogram has been used in terms of CPU to calculate. Then we extract the x-min and the x-max, which basically with the histogram is quite simple. We just do a for loop from 0 to 255, okay, and we stop at the first non-zero element. This, by the way, is the mean value of your image, and to have the max value, we do the inverse. We go from 255 up to 0, and we stop if we have something different than 0. This will be the maximum pixel in our image. Okay, all this because we need these as parameters for the histogram stretch algorithm, which is here again between start and stop timer, because we want to calculate the time that all these have to execute. Okay, now we prepare for doing the same stuff in hardware. Basically, we start by populating a vector in memory with our image. We do this because we're going to pass this address here to the DMA. Okay. This is a tricky point. Basically, let me jump here. As we use the BRAM broadcast, okay, that is going to split the stream between the do histogram and the do histogram stretch IP cores. Basically, all them need to finish their job. They cannot block, because if you block one, the other will be blocked as well. So these have the side effect that the histogram and the stretch IP cores will always be executing. Okay, so basically here we start the histogram because we want to calculate the histogram anyway, but the histogram stretch, okay, we put some crazy values for the max and min. Basically, don't care at this point the result because we just want the histogram, but we need to execute them anyway. Okay, so this part here is that you always need to do if you want to do a transfer, DMA transfer, at least a simple DMA transfer. Okay, we flush the cache. Okay, in this case the input and the output. Okay, we do the transfer. Here the image in is the array that has the image. Okay, and we do an operation DMA to device, basically going to push this data here through the DMA to the device, and then the opposite, device to DMA, and we write the results in this address here, DMA MDMA buffer, which again is defined here. Okay, let's continue. Then we do all these between a start and stop timer because we want to calculate the time. Then we extract again the min and max values of the image. Basically, this is also good because we want to validate the results of the histogram. And we do this again, just but now passing the x max and x min that we started before. Okay, I have already my Z board connected here. Let me check. Let's program it again just to verify. Okay. By the way, guys, by using the Z board or basically the Zynq itself, you can get this warning here quite a lot. Basically means that if you have any debug core that is waiting for a clock, you're going to get this warning, because basically the Zynq will not start its clock after he starts executing the program. Okay, so we come here now to Zynq SDK and let's run this program and see how it goes. Cool. Let me do a zoom here. So basically, we did the histogram in software. Okay, the histogram software execution time took 3 milliseconds. Okay. Then we did the histogram stretch in software that took more 6 milliseconds. Okay, and then we go to the hardware version. Okay, the histogram in hardware took 2 milliseconds. By the way, it's already faster, at least in 1 millisecond, than the software version. Then the histogram stretch in actually again 0.002 2 milliseconds. Okay, to execute. Basically, it will be more or less the same, because as we said before, for the hardware point of view, it's just a string that is passing to a filter. So there is no contention. Will just be more or less always the same. Then we created here a summary. Okay, basically this is the total time in software version that was like 9 milliseconds, and then the same thing in the hardware version that took 4. So basically a ratio of 0.44, almost half of the time. Okay, and then we just say that the software and hardware images are basically the same, because at the end we just compare. Here we compare if the stretched histogram are the same, the software and the hardware version. Okay, but in order also to see these results, we can come here and debug. Actually, I already teach how to do this, but it's always good to remember. Okay, we actually put a breakpoint at this point here, that is after everything has been calculated, and let's copy and paste some stuff. So here we save the file at this address. Okay, here is the XMD console, is where we can actually extract data from the Zynq memory. Actually, this works for Microblaze. And then we actually populate the file by reading this address. By the way, this address is the same address of our DMA out. Okay, these are the number of bytes that we need. Basically, if we come here and we multiply 240 by 320, is this. Okay, then we close the file. Okay, then let's just jump in MATLAB. Okay, first let's take a look on this file here. Okay, this is the file that we generated. Show in Explorer. Maybe if we come here. Okay, guys, these are the values that we exported from XMD. Okay, and I created here. Let me see if it's already open. No, it isn't. Yes, I created here a small app in MATLAB just to parse these values. Okay, and if you come here, parse file, and we point to the log that this log file that we populated, we have here again the image stretched. Okay, guys. So by the way, the source code of this will be given as well, so you guys can do it yourselves. Let me just jump again to the Zynq SDK. So basically that's it, guys. This is how we do, is a way to do a contrast adjustment in hardware. Okay, as we said, for small images we have this gain of 0.4, but if you use for instance HD images or something bigger than that, the advantage of doing this in hardware will be more and more prominent, will be way better. Okay, so hope you guys enjoyed. Let's finish this. Let's finish the day. Next video I probably going to show now how to do convolution, how to do an IP core that do 2D filtering, and probably this will be one of the last videos that we talk about Vivado HLS. Then we're going to switch to another topic. Hope you guys enjoyed. Give a thumbs up if you guys like the video, and see you the next week probably.